Hi again. My kid happened to come to me, so I just disconnected the video record. Sorry about that. Let me continue to talk about what I was talking about. So the unitable analysis of the NERS school data is a school. So the observation 81, the case number 81, the ID 81, that school is located in urban area, and the variable G10 urban is coded as 1 because it is urban. And 393, the case number 393 is coded as 2 because it is suburban. And the case 461, school is located in the rural area, which is coded as a 3. So for this specific variable in that NERS data, you see 1 or 2 or 3 for the cases. So, but this 3 does not necessarily mean higher than the number 1 or number 2, because this is simply a code indicating rural, and 2 indicates suburban, and 1 indicates urban, right? So this is just the categorical variable, even though it looks like a numerical value, but it's not continuous variable, or, this is not meaningful numbers. This is just simply a code, right? But the SPSS, the machine, does not know that. So with that reason, we want to convert the data into something that SPSS can recognize. So the categorical variable should be converted into multiple dummy variables. So a dummy variable is defined as a dichotomous variable, right? Which has only 2 options, 1 or 0, okay? So if, of course, you can have like 1 or 2 instead of 0 and 1, but at the time, the integer non-zero does not have any benefit about the convenience of the variable, because our goal is to remove the slope coefficient term by plugging in 0 when we have a reference group, right? So normally, okay, so G10 urban has 3 categories. So in this case, so let's say K is the number of categories. So how many dummy variables should we make? When we have a K group here, the category number is K, so in this case 3. So when we make dummy variables, how many dummy variables should we make? So K minus 1. So urban versus non-urban, suburban versus non-suburban, something like that. So for those, for both of the dummy variables, the reference group include a ruler, right? So when you have a ruler as a in the urban variable, in the categorical variable, so you should choose one reference group. Okay? So we're gonna compare the focal group versus reference group, and the other focal group versus reference group, something like that. So let me keep talking about this logic again and again, so I think you will be accustomed to the logic of dummy variables. You might feel tired of this logic. Still, why do we have to go through this complicated situation? And I'm just talking about this conceptual perspective on the use of the dummy variables. I will talk about the shortcut by using a GLM function instead of regression function later. But still, we want to understand the concept first. So, have you realized this slide set has a GLM here? Moscow, maybe. So I like GLM, yeah. Anyway, so when you make urban variable, dummy variable, and when you make suburban variable, this is the way how we code neutrally. And you have urban, so this is the urban variable, this is the G10 urban variable. So when you make a new variable for urban, since this is urban, 1 is coded as 1. And when you make a new variable, new dummy variable, suburban, since urban is regarded as a non-suburban, you're gonna code this as 0. Okay, I'm talking about this specific case. Okay, and the second row, case number 393, for urban. Okay, suburban is not urban. So suburban is a non-urban. So this is coded as a 0. Okay, and now when you create a suburban variable, then this case is coded as 1 because this suburban is a suburban, right? And then for this case 461, this is rural. When you make either urban or suburban x variable, x dummy variables, this rural is non-urban. Also, this rural variable is non-suburban. That's why this case is coded as a 0 and 0 for both dummy variables, respectively. Does this make sense? Dummy variables. So, when you have a variable G10 urban in your SPSS data set, the variable has 3 categories, 1, 2, 3, but there's no other response. So you have 3 categories, and when you see 3 categories, you will feel, okay, I'm gonna make 3 minus 1 dummy variables because here k is 3, so we're gonna make k minus 1 dummy variables. You can choose urban and suburban. In this case, the rural variable is a reference group. So once you make new variable urban, okay, this urban became 1, and again you're gonna make one more dummy variable suburban. This case, since this is coded as urban in terms of a G10 urban variable perspective, and this is gonna be 0 because urban is not suburban, right? So 0. Okay. Likewise, 2 other cases coded in this way. The suburban is non-urban, so 0. Suburban is suburban, so 1. Rural is non-urban, so 0. Rural is non-suburban, 0. Okay? We do not need a third variable x rural that represents as the rural. Why? When you have 2 cases, when you have 2 target groups, you just want to compare one and the other, right? One time. This is the concept of dummy variable. So when you have only 2 levels in gender group, female and male, so you just want to compare 2 groups at a time. So dummy variable does not, you don't need to make dummy variable when you have just two levels in the gender group, right? When you have more than two groups, you need to make dummy variables. Okay, so when you have three groups in G10 urban, you have to make two dummy variables because 3 minus 1 is 2. Does it make sense? The pair of values X urban, X suburban is different for each group of subjects. So we can tell three groups apart using two dummy groups, two dummy variables. All right. So before we had the equation a y hat equals b0 plus b1 x. In that case, x is a G10 urban variable. Now, since you made two different dummy variables, now b1 x G10 urban is split into two different dummy variables. So this b urban x urban plus b suburban x suburban. So we interpret B urban as the difference between urban schools and all others, holding X constants. So this is like playing as a role of control variable. And now this is your primary independent variable, something like that. Okay. So controlling for this, you want to know the mean difference between urban and the other regions. So B1 is mean difference, okay? For all the urban schools, X urban equals 1 and X suburban equals 0. So B0 plus B urban. For the others, X suburban equals 0 if they are rural, and X urban equals 0, therefore B0. X suburban equals 1 if they are suburban, and X1 equals 0, therefore B0 plus B suburban. So simply you just plug X suburban 0 here, then this is removed. This is eliminated. So you have B, just B0, right? Do you remember ruler was 0 and 0 for the pair X urban and X suburban, right? So 0, 0, you're gonna have a B0. Y bar equals B, which is the mean for rural. X suburban. So this is a suburban. So you plug this one, and this is constant, so you cannot remove this. Leave it alone. So suburban becomes 0 in this case because this is urban. So you plug 0 here, then what is the remainder? Y bar equals B0 plus B1. I mean B sub, right? So B0 plus B sub becomes the mean for suburban. Does this make sense? So what is the urban mean? Urban becomes this 1. This is not urban, so it becomes 0. So the mean for the urban is B0 plus B urban. Okay? Because of the way we created X urban and X suburban, we will never have a case where both X urban equals 1 and X suburban equals 1. Suppose now that we use the variables x1 and x2 in multiple regression in our estimated regression equation. So this is a general form of multiple regression. Remember that? So B1, B2 parameters, x1, x2, x variables, y hat, estimated y. So in this case, you plug the specific x variable, which is urban and suburban. You plug that here. Then now you got this one. This is a general form for multiple regression. So x can be either continuous variable or categorical variable. In this case, both of them are categorical variable, especially dummy variable. In the beginning, we had y hat equals b0 plus bx, right? That x was G10 urban. The G10 urban was a categorical variable which includes multiple categories. Since we have multiple categories in the one categorical variable, we need to have k-1 dummy variables. That's why we had this one. The value of B0 is the mean for the rural schools. We set it up, rural school, as a reference group, which is a predicted value of y when the values of all x's are 0. Yes, all x, you plug 0, 0 here, and B0 becomes rural mean. In a case such as this, we might actually be interested in testing whether beta 0 equals 0, because beta 0 represents the population mean of the rural school. So beta 0 is a population parameter. B0 is a sample parameter, estimated parameter. So beta 0 is rural schools mean in the population. Okay, with this intercept and two slopes, we can compute all of the group means. So you have B0 for rural mean. You have B0 plus B sub for suburban mean. You have B0 plus B urban for the mean for urban schools. Our estimated regression equation will be the slope B1 represents predicted change in y for 1 unit increase in x1, holding the other x variable. It is also the difference between the urban group mean and the mean for the reference group of rural group. So B1 is the difference between urban and rural schools. Slope B2 represents predicted changes in y for 1 unit increase in x2, holding x1 constant. And it is the mean difference between the suburban schools and the reference group of rural school. So B0, rural, B0 plus B1, urban, so y bar, this is mean value, okay, in the y. B0 plus B2 is suburban mean. So none of our cases ever has y bar, y hat equals B0 plus B1 plus B2. This is not never seen, because no school can be in 2 locations. Okay, so descriptive statistics. So G10 urban, when you delve into the G10 urban, the multiple categories, each school can show each mean. Okay, so urban schools are 327 and suburban 504, rural and 129. Okay, so why must be like some kind of score, right? Teacher community or whatever achievement score. So the schools that are located in rural area has a minus value. So this is a standardized score. So mean score is a 0, grand mean, and below the mean, negative value is indicated in the rural area. Yeah, it makes sense, right? Okay, so, and then now see, look at the regression analysis table. So this is just the descriptive statistics, mean, sample size, and a standard deviation. And this is regression table. So minus 0.298 is the mean for rural, which is the same as this. And then you're gonna add them up, because this is the mean difference between rural and urban. So if you sum them up, minus 0.298 plus 0.555, and you want to have this value, which is urban mean. Okay, here urban mean. And then minus 0.298 plus 0.422, which is 0.124. This is a suburban mean. So here suburban mean, 0.124. Okay. So slope shows just the mean difference. And this grand mean, in this case, grand mean means what? Population mean for rural schools, the reference group. All right, so now that we have seen that we can use dummy variables in multiple regression to represent groups, we will tackle another idea. Suppose we are examining a regression model with a dummy variable, and we expect that X relates to Y differently in our two groups. Say we are studying the prediction of the outcome of teacher community scores for public and private schools, and we believe teacher community relates differently to the predictor of principal leadership in the two school types. So we are learning multiple regression. So in addition to the school location, we're gonna add, in this case, we change the model or research topic. So here, school type, this is public school and private school. So now we want to add one more X variable, which is principal leadership. Okay, so we want to see this Y score, teacher community. Okay, so here interaction is interaction between school type and principal leadership. We can say that there is an interaction of school type and principal leadership with respect to the teacher community outcome. How can we tell if we need to be concerned about an interaction like this? One way to let SPSS help us find it by using the scatter plot. So yeah, scatter plot is very useful tool. Another is to examine the correlation or slopes. So let's look at that one by one. Pull down the graph menu and make a scatter plot where Y is the variable, teacher community, and X is principal leadership. Before you click OK, move the variable public into the set markers by box. So this is instruction of how to use SPSS to show interaction plot, scatter plot. So you're gonna show two different colors. You're gonna show two different colors of school types. And then you're gonna make two different regression lines. If they are like across each other, or at least disordered, like even though they do not cross each other, if they have different slopes, we have like a suspicious feeling in the interaction effect between the school type and the principal leadership. Okay, so let's keep reading this. So this forces SPSS to use different symbols for public and private schools and enables us to edit the plot, then use chart options to plot separate regressions for the school types. All right, so in this case, two lines are two different school types. So these dot, each dot represent individual school. In this case, we just see, oh, it looks like a linear, but we want to see the slopes, depending on the school types, can be different. So slopes pretty much parallel here, okay, parallel. So, I mean, this difference, starting point can be different, but that's okay. As long as the slopes are parallel, there's no interaction effect between the two x variables. Okay, so in this case, in this data set, so they are crossed each other. So difference of the principal leadership on one type of school is totally different from that of the principal leadership on the other school type. This is what it is about, okay? So I think this plus sign is for 0, so private school, and circle is around here, so circle is 1, okay? So the slopes, this is steeper than the other, this is flatter, okay? So I think, I don't know, if this is public school, looks like it, and this is a private school, so slopes is steeper in this school type, and this is flatter. Okay, teacher community, this is y outcome variable. Here is a plot for teacher happiness. Okay, this is teacher happiness, contentment with their job. As a predictor, this is x variable, not y variable, x variable. When we add the markers by public and plot, two lines, they cross. Yeah, they cross. So these lines appear to have somewhat different slopes. So there may be an interaction effect. There may be an interaction effect. So this is eyeballing method. So that's why it says there may be an interaction effect. So we do not know if there is an interaction effect until we take a test, statistical test on the interaction effect. So how can we do it? This is just a quick and dirty method. So based upon this, visualization, I have like a suspicious feeling about, okay, two different types of schools might have two different slopes, but until we take a test, statistical test, we cannot determine that for sure. So what we're gonna do is, do you remember the slopes here? interaction term is added in the model. Okay, so now you have a feeling, oh, why this interaction effect between principal leadership and the school type is added here is because we want to take a statistical test on the interaction effect for sure. So not just seeing the scatter plot, but also we need to know the statistical significance on the interaction effect. So at that time, we inevitably add the interaction term in our model, okay? So first variable and second variable, and the first variable, second variable, and then third variable. So we have three terms, 1, 2, 3, okay? So far so good, all right? Okay, so in order to see an interaction, are you going to run two separate regression analyses? No, we do not do that. We do not do that. We want to add one interaction term in multiple regression. Okay. To do this, we must split the file and run our model. Yeah, this is way too much complicated. If we split the data and, you know, to run the two different regressions separately, and that inflates type 1 error rate. We're gonna learn type 1 error rate a little bit later, but anyway, so many troubles if we split the data and if we run the regression analysis multiple times based upon the same data set. Yeah, we don't want to do it. We just simply add one more term, which is interaction effect term in our model, regression model, okay? Yeah, you can read this later, okay? You still want to read this one. Why do we have a lot of drawback to do that? Split the data and, okay? Yeah, this is not desirable approach. So instead of talking about this, let me jump this slide set. I'm afraid that you're gonna run the analysis in this way, but I don't recommend this method, okay? So here, look, two different regression models, so you don't need to do it. Okay, so more parsimonious solution is you're gonna add the interaction effect in your multiple regression model, okay? So forget about the slides, the page numbers 22, 23, 24, okay? And with the above approach, we run separate regressions for the groups involved if we see a potential interaction. However, a more parsimonious solution would be to model two slopes via an interaction in a single regression model. So when you have two solutions to resolve the problem, one simple way, two complicated way, which one do you want to choose to save your energy and time? Yeah, definitely. We want to go with a simpler way, which is a parsimonious solution. So when you think about the interaction effect between one and the other, you want to simply add one more term in the multiple regression, and you want to just conduct one regression analysis, okay? Also, this approach gives us a test of the interaction difference between the slopes. To do this, we need to compute an interaction variable. Suppose x1 is the public dummy variable and x2 is teacher happiness. Then we compute the product x3 equals x1 times x2. This new variable takes on values as follows. So x3 is 0 if the school is private. So here x1 is the school type. So private school was coded as 0 as a reference group, right? So if you have a private school, this interaction term becomes 0. And when you have a public school, plug 1 here, then x3 becomes x2. For the more elegant solution, we run a regression that includes x1, dummy variable, x2, continuous predictor, x3, interaction. So this is dummy variable and continuous variable. So in other words, covariate. So in this case, the teacher happiness. And this is teacher happiness times school type. School type dummy variable. So beta 1 represents the public-private mean difference. So this is dummy variable school type. So mean difference between public school and private school. And beta 2 is the slope of the teacher happiness, controlling for all other x variables. Beta 3 is the interaction between x1 and x2, or school type difference in the teacher happiness slope. So the slope of teacher happiness in the public school will be different from the slope of teacher happiness in private school in terms of y outcome. So interaction effect interpretation will be told a little bit later repeatedly. Yeah. Because x1 is a dummy variable, and also because x3 takes on the value 0 for private schools, the two school types have different models that we can determine even without running SPSS to estimate the model. x1 equals school type dummy variable, x2 covariate teacher happiness, x3 is interaction. The private schools, the value 0 is plugged for x1 and x3. So 0, 0, then they will be removed. So y bar equals beta 0 plus beta 2 x2. This is for private school, and the public school, x1 become 1, so nothing is removed. So plug 1 in x1 and then 1. So this 2 can be y-intercept, and nothing is removed in this case. And here, since x1, x2, the multiplication between x1 and x2 was the interaction. x1 had 1, so x1 part is gone, and now this, so this x2 is the same, right? So you make it in a parenthesis. Okay, so beta 0 plus beta 1, new y-intercept, plus beta 2 plus beta 3, this is slope for public school. Okay. From this output, we can see that the private school equation, we can compute the other model. Intercept is B0, B1, this. slope B2, B3, this, so everything is here. So once you have SPSS output, you can make your own equations. So now y hat for public school is minus 0.639 plus 0.592 teacher happiness. Okay, so here you see the slope happiness for private school is different from slope teacher happiness for public school are different. Okay. SPSS also then tell us whether the interaction is significant. So here, since we have 3 terms, public school, teacher happiness, and interaction. So interaction is here, and then interaction p-value is here. So based upon this SPSS output, even though we saw the visualization, the scatter plot shows like crossed between public school and private school. So we had a suspicious feeling about that, right? Interaction effect. However, when we ran the interaction analysis here, the p-value shows insignificant result. So when we have alpha level 0.05, so this is larger than 0.05, so we cannot reject the null hypothesis. This is not statistically significant. So what should you do? What should you do? So I will tell you the next time, okay? Thank you.